And while I'm thinking of it, some of you still need to come by my office and do that intro assignment. So don't forget about that. Today, if you have time and you still need to do it after lecture, that's where I'm going. So we could do that then if you wanted. Okay, so what I thought we'd do is take a running start at this last bit of material in this part to remind you that there's a difference when it comes to your measurements with regard to accuracy and precision. Accuracy, remember, can be depicted by all the darts hitting the bullseye, okay? Precision, it's possible to be pretty darn precise. That means your reproducibility or repeatability is good. Okay, so your precision is tight. So this guy has good precision, poor accuracy. This guy has good precision and good accuracy. I would argue there's one more scenario, and it goes like this, where you have the bullseye is where you're trying to get, okay? And if you have 5 darts that are just kind of all equally spaced like that, okay, you could figure out an average spatially, and the average would be here, okay? So to me, the average is going to give you good accuracy, okay? But the scatter makes it poor precision. It's a little bit different than that first one up there. All right, so again, we did this slide on Friday, but it's so important. This part of material is so important. I'm going over this with you, and then I'm going to assume that you're going to apply it to all the problems that we're working, okay? So I will grade your solutions to your homework according to applying these rules. And these are not my rules. Ultimately, my rules of rounding is what we're going to get to today. I didn't make these up. Sometimes students will say, how Mrs. Snipes, do you want me to round it? I'm like, well, how would the scientific community have you round it, okay? So when we write measured quantities down like 1.5 pounds, okay, or something like that, or 3.97 meters, okay, that last digit, okay, that trailing digit over there to the right, okay, that's where there is uncertainty, okay? So you can only report one uncertain digit. And so in the example, for instance, if you're measuring length and you have 2.95 meters, M for meters, okay, this is an uncertain digit. Okay, so I put a question mark over that. The other ones are hardcore. I know it's 2 in the ones place. I know it's 9 in the tenths place. But in the hundredths place, 5, there's wiggle room there. Okay. There are 2 types of numbers that have no wiggle room. Okay, they're called exact numbers. And they're either exact because you're counting a unit, like you're counting people. There's no uncertainty there. Or it's by definition. The one thing I told you guys you need to remember with regard to length between the English and metric system is 1 inch is equal to 2.54 centimeters. Remember I had a little arrow there? And exact, it's by definition. Somebody was thinking when they linked those 2 systems with regard to length. Another good example of by definition is within the metric system, the whole prefixes thing. For instance, I could say 1 kilometer is exactly equal to 1,000 meters. Like that's by definition, no uncertainty there, and that makes a difference. Because today we're gonna see that if it's an exact number, when you deal with it in a calculation, it brings no uncertainty to your calculation. So exact numbers are important. And then I'm almost done with the review slides. So we said, and today I'm going to show you how to look at a measured quantity with uncertainty in it, and we're going to count significant figures. And I'm going to use little check marks it's a significant figure. Okay, and these are the rules for counting significant figures. Just to remind you, if it's anything other than 0, it counts. Okay, the question usually comes with zeros, and if the 0 is between 2 digits that aren't 0, it counts. If the 0 is a trailing 0, and if it's after the decimal, it counts. Okay, now, if a 0 is a placeholder, it's important, but I'm going to try to prove to you why this is. It's important, but it doesn't count. An example of that fourth rule is 0.0075, okay? And this first 0 doesn't count, okay, because it's just, I'm trying to emphasize where the decimal is. And these two zeros don't count according to this right here. They are leading zeros after the decimal. Okay, they are not significant. So I put a check over the 7 and a check over the 5. So I have 2 sig figs here. All right, and I'm going to hit this hard in a minute, very shortly. This idea of, and I'll kind of put it up here to remind you what this means. So, for instance, what if we had a measured quantity, let's go with liters, and we'll say we have 1,340 liters. 1,340 liters. Okay? Same number. It's like I'm playing a magic trick, right? You guys would tell me, where's the 0 here? I mean, where's the decimal here, sorry. Where's the decimal here?
After the 0.
It is after the 0. So I'm going to put the decimal there, and since the person who gave me this volume didn't put the decimal, I'm going to go ahead and put a dot, dot, dot. This is my own convention around it, because I know, and you guys know, that it's implied. Okay. Now I'm going to rewrite this volume down here, and I'm going to say the person who got that volume went ahead and put the decimal there. Those are two different numbers in today's convention of the scientific community. This right here, if they put it on there, it is an explicit decimal. Those are two different numbers. Let me go ahead and kind of finish that thought, because it's not that complicated. So the convention is if the person cared enough to send this very best. No, if the person cared enough to actually use the ink to put the decimal there, what they're trying to say is the tolerance or the uncertainty starts at 1. Okay, so they're saying you can have one. You can carry one digit that is uncertain. So this is going to be significant. Okay, the convention here up here, if they didn't take the ink or the time to put the decimal, then we're going to say that the uncertainty begins here at the tens place. Okay, it's a different number. It's a volume measured to a different tolerance for uncertainty. Okay, so there's only 3 sig figs there, and there are 4 sig figs there. And the difference is an explicit decimal and an implied decimal. Okay, so that's the nutshell of kind of, in a nutshell, what I'm going to kind of talk you through. The term ambiguous means if somebody's ambiguous, they're like wishy-washy. Like, dude, can't you just say what it is? Okay, ambiguity. All right. So I'm going to try to kind of show you why these decimals, these zeros, these trailing zeros after the decimal are significant. Okay. So in other words, just to kind of use the convention I've been using with check marks and all that. Oops, let me kind of make it big. I would put 2 check marks there, 2 check marks, and actually this is a trailing 0 after the decimal. It counts. Those 2 count because of rule number 1, and these are 2 more trailing zeros after the decimal. They're different equipment. Okay, plus or minus 0.1, plus or minus 0.01, plus or minus 0.001. Okay, so we have 2 significant figures, 3 significant figures, and 4. You're like, why is that? Well, let's take a look at those 3 quantities again. And like I said, unless they went ahead and did the statistics with that particular analytical machinery and told you, you kind of estimate plus or minus 1 in the last uncertain digit, okay? So, like I said, plus or minus 0.1, plus or minus 0.001, and plus or minus 0.001. So, to get the relative uncertainties, what we do is we take the measurement and we divide it by the uncertainty. The measurement divided by the uncertainty, and the measurement divided by the uncertainty. Okay. So this is 2.5 divided by 0.1, which is 1 divided by 25. You okay with that? Move the decimal over? Okay, good. The same here. 2.50 divided by 0.001. I'm sorry, I'm taking the inverse of that. This middle one, 0.001 divided by 2.50. The other one, 0.00, sorry, 0.001. What's that? I said the second one wrong. Thank you. Yeah, this should be 0.01 divided by 2.50. Yeah. So they're different tolerances. We say that this has less uncertainty, makes sense, 1 in 2,500 parts, and this has more uncertainty. This is cheaper than that. Measuring equipment. Okay, so we got to count those. Okay, they will, what I say, propagate through your calculations. Thou shalt tell the truth, but thou shalt not lie on either side. Okay, here's why those placeholder zeros are not significant. Okay, the example I gave you was the 0.0076 or something like that. The 76 significant. Those placeholders or those zeros that are after the decimal in small numbers, they don't count. So, for instance, according to the rules I told you, each one of these measured quantities has uncertainty in that last digit, and in each of these cases, these down here, these zeros are not significant, Okay, so to kind of emphasize that, we'd say two significant figures, two significant figures. You get the idea. And two significant figures. And all of these are two significant figures. And I'll try to kind of, and in fact, I even kind of doodled it on my paper to kind of convince myself that they all have an uncertainty of 1 in 25 parts. Let's go ahead and take the extremes. Okay, and again, we're gonna come up with uncertainty by taking the wiggle room divided by the measured quantity. So in the first case, 25, uncertainty begins here in the ones place, plus or minus 1. Let's look at the other extreme, what we got? 5 zeros? Plus or minus 5, 6. Okay. All right. So the uncertainty is we take the tolerance, okay, divided by the value. Whoops. Okay with that? The tolerance divided by the measured quantity. Okay? So if you're counting zeros and all that, I can move this, I can multiply it by 10 to the 6th, basically. Okay? Multiply this by 10 to the 6th. And this can reduce to 1 in 25 parts. I had to convince myself of that. Okay? So in each one of these cases, these have the same relative uncertainty, two significant figures. Okay, ambiguity, right? Assuming that this is not an exact number. It's not by definition. Okay, let's say that, let's see, grams. We haven't picked on grams or kilograms. Let's say that somebody weighed something and it is 32,000 kilograms. Okay, so you're like, all right, I got that. Okay, but you don't know, and if they were kind of sloppy, which, you know, I can be sloppy too, and they weren't careful about relaying where the uncertainty is, you don't know if, you know at least there's two significant figures, okay? But you don't know if the uncertainty begins here at the 1000s, or does it begin at the 100s, and then you have 3 sig figs? Or does it begin at the 10s, and you have 4 sig figs? Or does it begin at the 1s? Okay, does uncertainty go clear here? And you're like, hey, so that's a question mark there, so I keep those 3 zeros. I have 5 sig figs. Get a knot. And this example I showed you over here actually is how we handle ambiguity. If they didn't care enough to put the decimal, then the last digit that's not a 0, that's where the uncertainty begins. Okay? And if the number is rounded to the 1s, okay, I guess, in this case, it's a very special case, isn't it? If it's a measured quantity with uncertainty out here in the 1s place, they better put the decimal. Sometimes you'll be in lab or do calculations when you know the uncertainty starts here in the 1s place, but that digit's a 0. Well, in order to relay that, you have to explicitly put the decimal. Okay, so that's how that works. All right, so no question about it then. The difference between the other number, the 32000, and the 32000 decimal, okay, is this: we know that there are 5 sig figs. Okay. One of the things about scientists, and it's exciting, I like things that are black and white, and most things in science are black and white. Okay. So we need to communicate. All right. So one more thing about counting significant figures. In physical science, in chemistry, we'll be dealing with big numbers and small numbers. And the best way we can handle those is to pack them up into scientific notation. I'm not going to belabor scientific notation, but that's one of the many things that are covered in your appendix. Not your appendix, but your appendix of your textbook. So once a number is packed up in scientific notation, what you do is you focus on what we call the coefficient. Okay, and over here, this is the exponent part. Okay, so you focus on the coefficient, basically. And you count sig figs according to the same rules. So if that's the case, can you see where this first one, oops, how many sig figs? Hold up your hands in the first number. I'm liking it. Yep, I saw 2. Sig figs in the second one, 3. How about sig figs in this one? Yay, very good. And last one? 5. Yep, you got it. Okay, so, but do you see where these are all the same magnitude of number? They're all the same number, but they're relaying different information with regard to the uncertainty in that measured quantity. Okay? They're the same, but they're not. All right. All right. So this statement on ambiguity and numbers with uncertainty goes back to this one. This basically says that if the decimal is implied, you go with the fewest number of sig figs. All right. So we'll be working on that throughout the semester. But okay. Now, I'm finally going to show you why you really care about counting significant figures in a measured quantity that has uncertainty. It comes down to rounding, quite frankly. And if you've had physical science before, you know that it can be, students roll their eyes at how am I supposed to round that, okay? Well, it depends. The types of calculations can broadly be broken into addition and subtraction, okay? That's one way you round, okay? And multiplication and division, that's another way you round. Now, in chemistry, we do a lot more of multiplication and division than we do of addition and subtraction. But with that said, I'm going to start with addition and subtraction. So addition and subtraction, you don't count significant figures. Like, dude, why did you do all that with significant figures? Well, it's coming. Addition and subtraction, you don't count significant figures. You count tens places. Okay? So what this says, and I'll kind of highlight, basically says if you're adding or subtracting, okay, what you do is you count the, let's see, fewest decimal places. So I'm assuming here that you have measured quantities that have like the 0.0005 or 0.13, like the decimal stuff out there. It's a slightly different variation if you have large numbers, okay, like if you have 2,300 plus 10. It's slightly different, but it's the same idea. It's fewest tens places, not tenths places there. But let me show you how this works. So, for instance, we have a very simple addition problem. Total volume here, okay? So this is a situation where volume has been measured, but two different measuring devices. Okay, it happens. So if we were counting sig figs, we would say what? 4 significant figures there, and we would say 3 there, okay? But since we're adding, we need to focus on decimals. So this is how this goes. Okay, with regard to decimals, do you see where we have 3 decimals there? And how many decimals there? 1. And in both rounding situations, whether you're rounding according to decimals, because you're adding and subtracting, or the other type of rounding, it's always conservative. You're always fewest. So this guy wins out. So bottom line, and I'm going to show you why that is, how the uncertainty, propagates. I like that word. And when I took physics years ago, there was actually the guy went through like a error analysis, and he used the word propagation all the time. So how the uncertainty propagates through this simple addition problem. So whatever our calculator says, we need to round to 1 decimal. That's it. I know it feels like I'm making more out of it than I should. But you know, if you're going to add things, what you do is you line them up according to the decimal. Now the red there is like my question mark. Okay, so I have, see why I put that one, that when we measure to the nearest, let's see, 10s, 100s, 1000s, measure to the nearest 1/1000th, that last digit, that 2 is hot, okay? This, where we only had to the nearest tenths, that 4 is hot. So then you bring them down and you line up the decimals, and if it's hot at all, if any of the numbers are uncertain, okay, it contaminates basically the whole column of numbers. That's the way to think about it. So bottom line is it comes down with, and thou shalt only have 1 uncertain digit. Okay, so we have to let those go. And it's the rules that you guys have grown up with. Since this is a 4 and this is less than 5, we're going to leave the 6 the way it is. Okay, the rules of rounding are similar to what you've grown up with. Okay, so this goes away. Oops, let's go back. So we just lop it off. 1 decimal. Okay, so that's it. Any questions about that?
What if it had been 0.50 instead of 0.642?
Instead of this one?
Instead of 29.642
Yep.
as your answer, what if it had been 29.650? Would you have rounded the 6 before it up or left it as a 6?
Here, I'm going to write this over here. So you tell me, what's the first number? Still that 3.242? What's my first my numbers to add?
29.642.
Okay.
If the answer to adding both of them together.
Right.
If the 0.642 had been 0.650.
Okay, and plus 3.242, like that?
No,
You'd round it up to 7.
you rounded up to 7. Okay. What I wanted to know is the answer up there.
Oh, I see. Okay.
Yeah. If it had been 5 in the 4th place.
Yes, very good. Yep. If whatever you added together ended up with a 5 there, yes.
Would
Yep.
you'd have rounded it up at that point?
Yes.
Okay.
You keep I kind of go from left to right. Actually, I'm not keeping significant figures. I would kind of emphasize that 1 decimal and then look beyond. And since it was 4, we left it as 6, but if it was a 5, we would have rounded up to 7. Very good, yes. Yep. Okay. So, more than likely, though, you're going to be adding and, multiplying and dividing numbers, okay? And in this case, you get to count significant figures, and you round your overall answer. Because haven't you done problems before where you have several terms? When I say terms, multiply together. You have 3, 4, 5 things that you're like, oh. So you go back and you revisit each one of those terms, you count significant figures, and you round according to the fewest. You round your answer. And I'm going to show you, like I did before, to kind of show you how that propagates through. So let's say you want to get the area of a rectangle, and you are given the two lengths, okay? And so we do a little bit of geometry in here, okay? So the area of a rectangle, you take the length times the width, okay? But the deal here is how many sig figs are there in this length, 12.34? Very good. 4 sig figs. How about this one? 2. Perfect. So we're going to plug those into our calculator. We could do that right now, okay? We're going to plug them in our calculator, and how are we going to round it? What did the previous slide say? Since we're multiplying, we're going to count sig figs and round according to the fewest sig figs. So how many sig figs can our answer have?
2.
2, exactly. Round to 2. That's it. Okay, so it's funny because, it's such an important aspect of working problems in physical science, not just chemistry, okay? And there's a reason for it. But it's really not that complicated. So let's look at an example. Let's look at this simple example of finding the area by multiplying the length times the width. So again, like we've been talking, those lengths have uncertainty in the last digit. That's why the red 4 and the red 1. Okay, and long multiplication. Okay, so you multiply through, gosh, it's been so long. But I would probably take, don't you take this number and multiply it through?
Yeah.
Good. And then you take this number and multiply it through, but you screwed it over. Okay. It's like kids these days. I don't know if they show this anymore. So then you kind of line them up, and notice then that we have a 4. Let me change the. Cool. So we have a 4 plus nothing is 4. 3 plus 4 is 7. 2 plus 3 is 5. 1 plus 2 is 3. And carry down the 1. With regard to turning red hot, okay, looks like almost everything turned red hot. Okay, except for that 1 digit. So it goes back to what we talked about earlier in this part, that you can only keep one uncertain digit. So the uncertain digit you're going to keep is that 3, and this is an example maybe of what Tyree was talking about. We're going to keep that uncertain digit, but since the number beyond it is a 5, we have to round that up. 14. And no naked numbers, okay? Don't forget your units, even if I do. Okay. So, any questions about that? We'll be talking more about units on Wednesday. All righty, well, pretty good. So just to summarize, and you might want to put this on your refrigerator. We first talked about addition and subtraction, and you round according to decimals or ones places. Just kind of quickly, I bet you guys are okay with this. Let's say we had kind of some large numbers like, 3,560 inches plus 1,300 inches. Okay. You guys would tell me the decimal is implied right here, right? Okay. So my uncertainty has to begin there. Does that make sense? So honestly, I can only keep here in the 100ths place. Does that make sense? Okay. So my calculator would display 0.684. Okay. But inches. How do I need to round this?
You round it up.
Round it up, very good. So it'd be 4,900 inches. Does that make sense? Okay. It's similar to counting decimal places, but it's good. So we do a lot more in chemistry of multiplying and dividing, and in that case, you have a whole string of stuff. Well, you can have a whole string of stuff added or subtracted, the same thing. Whole string of stuff, you just look at the end. When we work problems in class, we're going to be rounding according to these rules. And don't forget that if somewhere, especially when you're multiplying or dividing, if somewhere in your string of terms, and it definitely happens, for instance, if you have the relationship between a meter and a kilometer, somewhere in your multiplication, things are going to multiply together. That's an exact relationship. There's no uncertainty brought by that. Okay, so that one you can throw overboard. So let's take a look right quick at these problems. These will be due on Wednesday. And I think I have, some of you guys saw I brought up the, this is my online, my e-text. So let's see. Sometimes it helps just to take a look. Starting with 19, wasn't it? Oh. I think you guys will do fine. I just like to double check. Okay, so 19 says express these, round them to 4 significant figures. You guys should do fine. Was it 21? Gosh, you guys have the answers to those.
19, 20, 21, 22, 23, and 24.
Okay, good. So you have the answers to some, but not to others. Remember, and I'm not complaining, but don't forget you can download from Doc Sharing the answers to the odd problems. So what the heck, you know? Are there any questions about those? What gets difficult is where you have multiplication and division and addition and subtraction. But I'm going to let you go for that, okay? All right, let's just stop there, shall we? I think so.